Hi everybody. We're starting a new chapter, Chapter 8, Further Applications of Integration. And the reason it's called Further Applications of Integration is in many ways this is a continuation of Chapter 6. If you recall, Chapter 6 was just applications of integration, and that's where you learned how to take solids of revolution and find volumes of them and find work and find a couple of different things using integrals. So what we're going to be doing is continuing our study here. The reason the book broke it up like this is because Chapter 7, we learned a whole bunch of integration techniques that we can now apply in this new chapter for more applications. So we are going to do section 8.1 right now, which is arc length. So given a continuous function f of x on a closed interval a to b, we are interested in finding the length of the curve. Okay, so let's give an example of what this kind of thing looks like. Let's do on the next page. So here's A and here's B, and let's say that we have some sort of a curve, right? And so we are actually interested in figuring out the length of this curve. So a natural question to ask here is, what does length even mean, right? I mean, we have kind of a notion of this. Maybe we could ask, we could say something like, well, if you were walking along that thing, how long would you walk, right? Or how far would you walk, rather? Or if that were a string, if we straightened it out, how long would that string be? So, question then, what does length mean? So here is the way that we are going to break this up. So as usual, we're going to partition A to B into n subintervals x naught, x1, all the way to xn of equal with delta x. So this is what we usually do, and I'm going to draw a picture here. I'm only going to chop it up into 4. I'm going to do a very small, sorry, let me back up here. Let me do it more equally. I'm going to do a very small subdivision so that we can easily see what's happening. So the delta x's are what separate these things, right? And so this would be considered our x0, this would be x1, this would be x2, this would be x3, and this would be x4. So question then, so let me keep going here, sorry. One more little thing here. Each of these guys corresponds to a point on the curve, doesn't it? Now, we still have not discussed, though, how to actually define the length. So here's going to be our strategy, okay? What we can do is we can call these guys points. So this could be considered point 0, this would be considered point 1, point 2, point 3, and 0.4. And what we could actually do is connect these guys with line segments. Let me do this more straightening. Oh, you know what? I'm going to do... I know, yeah. That's good. Let me actually do this, and I'm going to do straight red lines here. There we go. So these 4 red lines there, those are line segments that connect each pi to pi plus 1, right? So what we could do is we could add up all those lengths, couldn't we? So let me write this on the next page. The way we could do this then is define length as equaling, you take each line segment and you add up all the distances that you see. But of course, we know that that doesn't make it precise. So the way we make it precise is to do the limit as the number of partitions goes to infinity. Okay? So what we're going to do then is we're going to take the time to figure out what one of these lengths is, and then we'll be able to give an easy explanation for this, okay? We'll be able to come up with a formula that works. So this is what we need to do, okay? So let's go back to the page before, right? What are these coordinates? Well, this coordinate, for example, would be x2 and then f of x2. This coordinate would be x3, f of x3, right? And so we could just use the distance formula, couldn't we? We know that the distance formula is you take the square root and then you subtract the x's and then you subtract the f's and you square both and then you add them, right? So if we were doing this with the ith one, it would just look like this. The square root of xi minus 1 squared plus, and then f of xi minus f of xi minus 1 squared. Right? It would be all of that stuff. Now, we actually have something called the mean value theorem. So the mean value theorem is actually going to allow us to write this in a nicer way. So since f is continuous on xi minus 1 xi, the mean value theorem says there exists some xi star somewhere between xi minus 1 xi such that f prime of xi star is equal to the slope of the secant line. Well, what are we really saying here? If we were to go back to this example, what we're saying is that on each one of these, there exists some point where the tangent line on the curve is actually parallel to the slope. The tangent line there is parallel to the secant line that connects the two dots. Right? Do we agree that that happens everywhere? Think about it. If I look at my picture, that's going to happen there. If I look at this picture, that's going to happen there, right? This is always guaranteed by the mean value theorem. And so what we're going to do is wherever that occurs, that's going to be our xi star. So for example, that dot right there, this is going to be considered my x1 star. This dot right here is going to be considered my x2 star. And for example, on this one, it's way over here. This is going to be my x3 star. So that's where all my representatives are that I'm choosing for this representation. Okay, so because this is true, this actually means that f of xi minus f of xi minus 1 is equal to, so all I'm doing is I'm taking this fraction and I'm multiplying it by xi minus 1. So if I do that, I get that guy. And then on the other side, I end up with f prime of xi star times xi minus 1. So we're going to continue on with this, okay, up here. So what does this guy, so we're continuing with this on the next page, okay? So what does that radical equal? What I can do is I can replace now this difference that's inside those parentheses being squared. Or you know what? I wrote that wrong because the square should be here, right? So yeah, there we go. So what I'm doing is I'm replacing what I just underlined now with this because that's what the mean value theorem says that I'm allowed to do. So let's go on to the next page. This implies that pi minus 1, pi, the distance, is actually equal to the square root of xi minus 1 squared plus, and then we have f prime of xi star squared times xi minus 1 squared. Okay, I'm hoping we all see that. All I did, this red underline thing, is what I replaced this guy over here with, right? So I just took this guy and replaced it with this. And then I squared it. But what is this equal to? So I want to remind you guys of something. Doesn't xi minus 1, isn't that the same as delta x? That's just the change in x, isn't it? And so I can rewrite this in a nicer way. Here's what it becomes. It becomes delta x squared plus f prime of xi star squared, and then delta x squared again. But what does this equal? So can't I factor a delta x squared out and pull it out of the radical? And that's actually going to become, so what's left after I pull that out of the radical? I just have a 1 plus, and then I have f prime of xi star squared. And then what's left? I have a delta x that is outside of the radical now. So remember, all of this is really this. So I have simplified it as much as I could. So now what this means is that length is equal to the limit as n goes to infinity of the sum from I equals 1 to n of this guy that I just wrote down, 1 plus f prime of xi star squared. Sorry, this whole thing should be squared. It's easy to forget parentheses here when you've got so many, right? And then I have the delta x. But we should recognize this guy on the right. Because there's a function of xi in here, and then we have a delta x as well, this means that we can write it as a definite integral instead, And so we end up with the following formula. This is the integral from a to b of the square root of 1 plus f prime of x squared dx. And this becomes our length formula, or arc length formula. It's however you want to call it. Okay. So this is the length, of course, if f is, let me write it this way, f of x is continuous on a to b. And in other words, if you have a continuous function on a to b, you can find its length by using this formula. Okay, so note, what if instead x is equal to g of y, and this guy is continuous when y is between c and d? Then the length is given by the exact same formula, except everything is going to be in terms of y. Oh, sorry, not g of y. I apologize. I meant it's the same formula as in the last one. Okay? So what we're saying is, if you have a function of x and you want its arc length, you use this formula. And if you have a function of y and you want its arc length, you use this formula. The only difference in the two formulas is that one is in terms of x and the other one is in terms of y. Okay? All right, so let's see some examples. One thing I should note actually before we do these is be careful with the algebra. Do it in steps. In other words, first you want to find the derivative, then take the derivative squared, then take the derivative squared and add 1, and then finally take the square root of the derivative squared plus 1. Okay, you've really got to do these step by step. Believe it or not, each of these steps can be algebraically complex, okay? So do it slow, do not rush it. All right, let's get started with some examples. So number 1. Find the exact length of y equals x cubed over 3 plus 1 over 4x for x going from 1 to 2. Okay, this is a great example because the algebra, we actually have to be very careful as we do this. I'm going to do it all in steps. So let's start with finding the derivative. What is the derivative of this? So when you look at 1/3 x cubed, if you bring the 3 down, it actually cancels with 3 there. And so I just get x squared. And then isn't this term the same as 1/4 x to the negative 1? Right? And so if you take the derivative of that, you actually get negative 1 over 4x squared, right? Minus 1 over 4x squared. Now, what I'm going to do is I'm going to actually combine these two fractions together, right, using algebra. So what would this be? So I know that if I have x squared over 1, the lowest common denominator is 4x squared. So I'm going to multiply this by 4x squared and this by 4x squared. And so what I end up with is 4x to the fourth minus 1 over 4x squared. That's what we get. Next, we're going to do the derivative squared. So we're going to square all of that. Now be very careful, right? To square a binomial, you have to have 3 terms, right? You can use FOIL or you can use your formulas. So if I square that, I get 16x to the 8th on top, and then minus 8x to the 4th, and then plus 1. Over, and then if I square the bottom, I get 8, oh, sorry, not 8. I get 16x to the 4th. Okay, so this is what I get so far when I square the derivative. Now, I need to add 1 to the derivative. Seems silly that I'm going to add 1 in another step, but the reason is because I'm actually adding 2 fractions together here. So what is 1? 1 is actually 16x to the 4th over 16x to the 4th. I got a common denominator again, and I'm adding this fraction to it. So what do I get if I add these two? Well, if you add 16x to the 4th to negative 8x to the 4th, you actually get positive 8x to the 4th. So it becomes so this is what I get. Okay, now the reason why we have to take the time to do this is we're about to take the square root. And so what we want to do is look at this guy and ask ourselves, does this factor into something nice? And I want you to notice something. Doesn't this and this look almost identical? The only difference is that we have a plus here, and over here we had a minus. And don't forget where we got that from. Wasn't that equal to this guy up here squared? The guy from before? So actually this new guy is also a perfect square. I can write it this way. Okay. This is the key. If you don't notice this is a perfect square, you're going to have issues with the next step. But this is the important part, because we're finally now ready to take the square root. Let's back up. Remember, we're using this formula. And so we now need to take the square root of all of that we just did. Okay? So the square root of 1 plus f prime of x squared is equal to the square root of what we just got, which is 4x to the 4th plus 1 squared over, and then we had this was 4x squared. I forgot to write that down. I'm writing that down because we're about to take the square root of that, right? So, of course, since these are both perfect squares, you end up with just 4x to the 4th plus 1 over 4x squared. Which is actually x squared plus 1/4 x to the negative 2, okay? That was a lot of algebra, but now I'm ready to actually solve the problem. The problem will be easy now because I know I'm going to integrate from what? Remember, I'm going from 1 to 2, and I'm going to integrate this, but it's really just the integral from 1 to 2 of the answer that I got from all that algebra. Right? Because I've already done all of the square rooting, I did the squaring, I did everything. And so now I'm ready to take the antiderivative, and that's actually not a difficult antiderivative to do. So using the power rule on that, I get 1/3 x cubed. And then the next one, if I add 1 to the power and then divide by that, I actually get minus 1/4 x to the negative 1, and I'm going from 1 to 2. So if I plug in 2, I end up with 8 over 3 minus 1 over 8. And if I plug in 1, I get 1/3 minus 1/4. Okay, so let's go ahead and put this in the calculator and see what we get. I'm literally doing this as we speak. So we have 8 thirds minus 1/8 minus 1/3 plus 1/4, and we get 59 over 24. Okay, and so this is the exact length of that curve from 1 to 2. You could see all of this work was algebra, but we're doing this again so that it'll be something that is easy to integrate and we won't just stare at it and not know what to do. Okay. All right, let's try another example. So this is going to be number 2. Find the length of the arc of the semi-cubical parabola y squared equals x cubed between the points 1, 1 and 4, 8. Now, you'll notice, by the way, that we do not have one variable in terms of the other here, right? We either need to solve for y or solve for x before we proceed here. Which one should we do? Well, if we try to get y by itself, we're going to have to deal with a plus or minus there. And so that might be a little tricky. Or if we deal with the x, we could just take the cube root of both sides, and that might make our lives a little easier. So let's go with that. So this implies that x is equal to, if I take the cube root of both sides, I get y to the 2/3. And what's y going from? Y is going to go from 1 to 8, right? I'm just looking at these values because I'm looking at the y values and what they range between. Okay, so let's go ahead and remember our formula. We know that we're going to do the integral from 1 to 8 of the square root of 1 plus g prime of y squared dy. So as before, I'm going to do all of this I'm going to do all this algebra separately here. And let's actually see what we get. So since g of y is equal to y to the 2/3, let's go ahead and do g prime of y. So the derivative. The derivative would be 2/3 y to the negative 1/3, right? Now we're going to do g prime of y squared. So if we square that, we actually get 4/9 y to the negative 2/3. Now if we add 1 to it, we end up with the common denominator. So this actually looks like this, 4 over 9y to the 2/3, right? And so if we're going to add 1 to that, it makes sense that we're going to write 9y to the 2/3 over 9y to the 2/3 plus 4 over 9y to the 2/3. So if we add those together up top, we get 9y to the 2/3 plus 4, and the bottom we get 9y to the 2/3. Is this a perfect square? It is not, unfortunately. The bottom is, but the bottom is, but the top is not. So if we take the square root of 1 plus g prime of y squared, what do we end up with? Well, unfortunately, the top remains a radical, but the bottom actually does come out of the square root. It becomes 3y to the 1/3, right? The power gets cut in half. What does this equal? I'm actually going to write it this way. Now, actually, this is as much as I can clean this thing up. Unfortunately, that second term is not a perfect square. Okay? You cannot factor it, so it's not a perfect square. So here's what I'm going to do then. This is going to be what I'm going to integrate. So let's go back to the first page. I'm going to write that in here. My integral then is going to go, it's 1/3 y to the negative 1/3. And then it's the square root of 9y to the 2/3 plus 4. And then I have dy. What am I going to let u equal? So this is actually a u substitution, believe it or not, because here's what you can notice. The derivative of the inside is actually that outside term, isn't it? Because remember, you're going to subtract 1 from the power, and if you subtract 1 from y to the 2/3, you actually get y to the negative 1/3. So we're going to let u equal 9y to the 2/3 plus 4. So then what would du be? Du would be, if you take the derivative of that, you get 18 over 3, so that's 6y to the negative 1/3 and then dy. Or 1/6 du is y to the negative 1/3 dy. So what does this equal then? I have a 1/3 and I also have a 1/6 now, so this is going to become 1 over 18. I'm going to pull that out of the integral just so I don't have to look at it for a while. And I actually have u to the 1/2 du. What do I do about the limits of integration though? Instead of going from 1 to 8, I need to plug those into my u equation there and see what we get. So if I plug 1 in first, 1 to the 2/3 power is 1, times 9 is 9, plus 4 is 13. So this is going from 13 to what? So if I plug in 8 now, what's 8 to the 2/3? The cube root of 8 is 2, and then 2 squared is 4. 4 times 9 is 36. 36 plus 4 is 40. So I'm going from 13 to 40 now. So this integral should be much, much easier. What is the antiderivative of u to the 1/2? It's going to be 2/3 u to the 3/2. So now I have 1/18 times 2/3 u to the 3/2, and I'm going from 13 to 40. Let's do some simplifying here. 2 and 18, that becomes a 9. So I actually get 1 over 27. So you get 1 over 27 times 40 to the 3/2 minus 13 to the 3/2. What is something to the 3/2? So look, anything to the 3/2 is that. So let me show you. Anything to the 3/2 is the same as a root a, right? Because we have a to the 1/2 times a to the 1/2 times a to the 1/2, or a times a to the 1/2. And so here's another way we can write our answer. 1/27 times 40 root 40 minus 13 root 13. So that would be the length. Before I go on, I should note that the integral that you end up with, so let me say something here. So tip, these problems should always end up with an integral you can solve. If it doesn't, you probably made an algebraic mistake. So the thing I'm trying to point out here is that these problems are cherry-picked, okay? Because when you go back to the original formula, this thing in here is actually pretty complicated. If you just try this for any random function, you're probably not going to be able to solve the integral. So these problems are very much cherry-picked so that it is something that you can work through easily once you do the algebra right. So if it doesn't work out nicely, it means you probably made an algebraic mistake somewhere. Okay, so let's try another example. This will be number 3. Find the length of x equals ln of cosine y from the point 0, 0 to the point ln of 1/2, comma, pi over 3. We've already got our function in terms of y, don't we? So it makes sense to just look at the y values here and deal with it that way. Okay, so the length is going to equal, we're going to integrate from 0 to pi over 3, and what we're going to have to integrate is the square root of 1 plus g prime of y squared dy. Okay, so again, I'm going to do this on the next page. Let's see what that guy becomes. So remember, x is equal to ln, so g of y is equal to ln of cosine y. So we start by taking a derivative. So the derivative of this would be 1 over cosine y times negative sine y, right, with the chain rule, which is the same as negative tangent of y. Let's go through the algebra some more. Then we have to square it. So if we square that thing, we actually get tan squared y. And then if we add 1 to it, we actually get 1 plus tan squared y. But guess what? That simplifies. If you remember your Pythagorean identity, that is secant squared y, right? This is the Pythagorean identity. So now we can take the square root of 1 plus g prime of y squared. So that's going to be the square root of secant squared y. Now we need to be careful. This is not secant y, but it's the absolute value of secant y. We need to keep the absolute value, right? Because this is a definite integral. We're actually integrating from something to something, so we have to keep that absolute value. We need to be sure that we are staying positive the entire time. So now that I've taken the square root, I'm ready to write down my integral then. It's going to be the absolute value of secant y dy. Now, can I actually get rid of the absolute value here? Well, it depends on the sign of secant between 0 and pi over 3. But that's in the first quadrant, isn't it? So let's write this down. We know that in quadrant 1, the absolute value of secant y is just secant y, since secant is positive there. How do you remember that? Well, remember, secant is the reciprocal of cosine, and cosine is positive there, right? Actually, all trig functions are positive in the first quadrant. So if you just remember that fact, then you're fine. So that means we're really just integrating from 0 to pi over 3 of secant y dy. That is one of the antiderivatives you should remember. We talked about that in 7.2, but this is going to be the ln of secant y plus tan y, and we're going from 0 to pi over 3. So what does this end up being? This ends up being ln of absolute value of secant of pi over 3 plus tan of pi over 3 minus ln of secant 0 plus tan 0. What is secant of pi over 3? So I never memorized other than the main trig function. So what's cosine of pi over 3? Cosine of pi over 3 is a half, so secant of it would be 2, right? What's tangent of pi over 3? Maybe we can write down a triangle here. So when you have pi over 3 right here, then this would be your 1, your 2, and your root 3. Or maybe I should have done that from the beginning, right? So tangent of that guy would be just root 3. So that means you get 2 plus root 3. You'll notice I got rid of the absolute value because 2 plus root 3 is a positive number. And then what happens here? Well, secant of 0 is 1, tangent of 0 is 0, so you get ln of 1, which is just 0. And so this is your final answer. Ln of 2 plus root 3. Again, these integrals have a really nice way of working themselves out. If not, something is wrong somewhere, so you just have to find your mistake wherever it is. It's probably somewhere in the way you set your problem up. Or it could be in the algebra. Okay, so the next thing we're going to talk about is the arc length function. We're doing the arc length function now, which is going to be the last idea we learn in this section. Okay. So suppose we fix an initial point f of a, and we wish to find the distance along f of x from x equals a to x equals b, x equals a to x equals c, and x equals a to x equals d. In other words, what if they asked you for the same function to find 3 different lengths? It doesn't make sense, since they all start from the same number, a, that we would just do this integral 3 times, right? So let me draw a picture of what we're talking about. So if we have our curve, and that's A, and that's B, and that's C, and that's D, I want you guys to picture that we want to find 3 different lengths there from A to each of those ending points. Okay. So rather than doing the same integral 3 times, why not just do it once for x equals a to x equals t, and then just plug in values for t later? That makes sense, right? Just create a variable there. So we're going to plug in the value for t at the end once we get our function. So this leads us to something called the arc length function. We use the letter s, so s of x, and this is becoming now the integral from a to x of 1 plus f prime of t squared dt. Now this should look familiar. This looks just like the arc length formula, except we are not using a b anymore. We're now using the variable x. So x now stands for the ending point, right? X stands for where we stop. And so what is t then? T is just our new input variable for the function, because we can't use x to represent 2 different things. So this, what we just wrote down, this entire formula, this is the distance from t equals a to t equals x along the curve f of t. Okay, so we're going to do an example. So this is going to be example 4. Find the arc length function s of x for the curve y equals 2x to the 3 halves with starting point 416. And also, this is a 2-parter, so let's call that first part part A, and this will be part B. Use it to find the length of f from 416 to 954. All right, so we have our curve y equals 2x to the 3 halves. So what we're going to do is we're just going to replace the x's with t's, just so that we don't repeat our variable usage, okay? And our starting point is 4, right? So this means that our s of x, we know, is going to be the integral from 4, that's the starting value, and then we're ending at x, and then we're going to have the square root of 1 plus f prime of t squared dt. And so I need to figure out what that is on the next page here. So what is f prime of t? Let's write down f of t first. F of t is 2t to the 3 halves, right? It's our function. Again, I just replaced my x with t's. So what is f prime of t equal to? F prime of t is 3t to the 1 half. And then what's f prime of t squared? This is just going to be 9t, right? Because if you square t to the 1 half, you just get t to the first power. and then we're going to add 1 to it. That's going to just be 1 plus 9t. And then finally, we're going to take the square root. This is not a perfect square, so we have to leave it as square root of 1 plus 9t, but that's actually not that hard to integrate, right? That's just 1 plus 9t to the 1/2. So we're going to write that on the previous page, okay? So 1 plus 9t to the 1/2. So we're integrating from 4 to x, 1 plus 9t to the 1/2 dt. So what is the antiderivative of, oh, I wrote that wrong. The 1/2 power should be on the outside, shouldn't it? That would have changed my problem entirely, so. Okay, so if we do the antiderivative of this, we end up with 2/3 times 1 plus 9t to the 3/2, and we're going from 4 to x. So if you plug that in, if you plug x in, you actually get, let me just go ahead and factor the 2/3 out. If you plug in the x, you get 1 plus 9x. Oh, I forgot something, right? I forgot to divide by the slope. Remember that you have to divide by the slope when you do the linear substitution trick. So actually, we do also, because we had a slope of 9, I have to multiply it by 1/9. So actually, we get 2 over 27, don't we? 2 over 27. So we get 1 plus 9x to the 3/2 minus, and then if we plug in 4, we get 9 times 4 is 36, plus 1 is 37. So we get 37 to the 3/2. So that's our answer. Let me write that down. That's fine. This is, I don't have to rewrite it. This is my answer to part A. What about part B? Part B is asking us to find the length of the curve f from 416 to 954. So we're ending at 9, aren't we? So remember, our arc length function just requires us to plug in the x value that we want to stop at. So if we do that, that means we're just going to do s of 9. So let's go ahead and rewrite s of x so that we have it handy. So this is for part B. S of x is equal to 2 over 27 times 1 plus 9x to the 3/2 minus, and then we have 37 to the 3/2, right? So all we have to do now then is, since we're going from 4 to 9, is plug in 9. So what happens when you plug in 9 into your function? You end up with 2 over 27 times, if we plug in 9, we get 82 to the 3/2 minus 37 to the 3/2. Or if we want to write that without 3/2 powers, we can do that. This is the same as 2 over 27 times 82 square root of 82 minus 37 square root of 37. And there you go. So an arc length function is just another way to do these problems. It's actually a little more work if you're only going to find one distance like we just did. But if you were asked to find several distances, all with the same starting point, then this, of course, would save time. The last thing I want to talk about is some useful notation. So I want you to recall from Calc 1, the fundamental theorem of calculus, part 1. It says that the derivative of the area so far function, that's what I call it, right? It's the area under a curve so far from a to x, is just equal to f of x. So what is the derivative, right? What is the derivative of the arc length function? This means that we're taking the derivative of the length from a to x of the square root of 1 plus f prime of t squared dt, right? What would the derivative be? Using the fundamental theorem of calculus, that just gives me the inner function with an x instead of a t. Okay? So what does this imply? This means that ds dx is actually equal to the square root of 1 plus f prime of x squared. What we're going to do, some useful notation then, since this is true, is to write it this way. ds is just equal to 1 plus f prime of x squared dx. This is an extremely useful piece of notation, and so this actually means that my length formula becomes easier. It's just equal to the integral from a to b of ds. Okay, so ds is that entire radical, square root of 1 plus f prime of x squared dx. What is another useful piece of notation? This is a way that it can help you remember it. So another note, more useful notation. I want you to think in your mind that dx squared plus dy squared is equal to ds squared. Okay? If you think of it that way, then this means that ds is really the square root of dx squared plus dy squared. Now, this is better than you think, because if I factor out a dx squared from this, doesn't this become that? So this is if I factor out a dx squared from the radical, right? And what happens if I factor out a dy from the radical? I get 1 plus dx dy squared dy. And so this is if I factor out a dy squared. And so what this is saying is that the integral ds equaling length is actually true regardless of which variable you choose to integrate with respect to. So this helps us remember the formula. Not only does it help us remember the formula, but in this class, we are going to use this ds quantity more times. It's not just this time, and you're even going to see it again in Calc 3, and you're going to extend it to more dimensions. So I highly recommend learning your arc length formula with respect to this ds quantity. I promise you won't be memorizing it just for this lesson. Okay, guys, that is it for this video. Thank you so much for watching. Hope it was helpful.